Hey guys, welcome back to some more A-level maths fun. In this video, we're continuing on with some proof by exhaustion examples. So, hopefully you've come here from the introduction to this concept. If not, maybe go back one video and check him out first. So, we're going through 4 examples. I've designed them, so hopefully they build up in difficulty. The very last one, the 4th one, is from my university notes. So, it's a question that I had to do in my first year of uni. So, probably quite tricky, but it's a good showcase of how powerful this technique is. So, without further ado then, let's get cracking. Okay, example 1. So our statement, or our conjecture, that we're trying to prove is that the sum of any 2 consecutive square numbers between 1 and 100 is odd. So sum means to add together, consecutive means one after the other. So we don't need to do anything too tricky here or anything too smart or out of the ordinary. I reckon first of all, let's list the square numbers that we are interested in. So we got 1, 4, 9, 16, 25, 36, 49, 64, 81, and 100. So those are the guys that we're interested in. Now we just need to go through each of our sums of consecutive square numbers. So, first one, 1 plus 4 is 5. Second one, 4 plus 9 is 13. 9 plus 16 is 25. 16 plus 25 is 41. 25 add 36 is 61. 36. Stylus is starting to give up on life. 36 add 49 is 85. 49 add 64 is 113. 64 add 81 is 145, and finally 81 add 100 is 181. So there we've exhausted every possible situation. We've shown for every sum of 2 consecutive square numbers between 1 and 100, they are all odd. So we can say every sum is odd. So our conjecture is true. And then we can mark a cheeky little QED on the end. Quite enough done. Okay, example 2, so a little bit trickier than example 1, although we did do one just like this in the introduction video. Except there we did it with 79, here we're doing it with 101. So, we want to prove that 101 is a prime number. So remember, with a prime number, a number is prime if and only if its only two factors are 1 and itself. So potential factors of 101 are every number less than it other than 1. So using proof by exhaustion, do we want to test all of those numbers? Hells no, we definitely do not. So we are going to use another trick for this one. It's the same trick we used in the introduction video. So first of all, we are going to consider the two square numbers. Well, one square number that is smaller than 101 and the square number that is bigger than 101. So if we put 101 in the middle of an inequality, we can say 101 is bigger than 100, which is the closest square number smaller than 101, and then it's smaller than 121, which is the first square number bigger than 101. So if we now square root throughout, we get 10 is less than root 101 is less than 11. So we know that the square root of 101 is somewhere between 10 and 11. Now remember, we know root 101 times root 101 is equal to 101. But 101 is not a square number, so root 101 is some irrational number between 10 and 11. So why have we done this? Well, factor pairs work so that as one side of the pair gets smaller, the other side gets bigger. So, for example, here with root 101 times root 101, if there was a factor of 101 less than root 101, there would have to be a factor bigger than root 101, so those two factors would multiply together and give us 101. So instead of taking into account every potential factor less than 101, we actually only have to worry about the numbers less than or equal to 10. And then if there was a factor either less than or equal to 10, that would tell us, well, there also has to be a factor then greater than or equal to 11. So, if we now just start with the smallest possible potential factor, which would be 2. So, if 2 was a factor, 101 divided by 2 would be a whole number. But 101 divided by 2 is 50.5. Now this implies then 2 isn't a factor. Now even more than that, the fact that 2 is not a factor actually tells us 2, 4, 6, 8 and 10 are not factors. How? Well, if either one of 4, 6, 8 or 10 were to be a factor of 101, then 2 would have to be a factor because 2 is a factor of 4, 6, 8 and 10. So already there we've got rid of 5 potential factors. Good times. So the next one to try would be 3. So if we do 101 divided by 3, we get 33.6 recurring, which isn't an integer, so that implies 3 isn't a factor. Now that has also now told us 3 isn't, we already knew that 6 isn't, but 3 not being a factor also tells us 6 isn't, and also 9 isn't. So none of those are factors. Okay, what's the next thing we need to try then? 5. So we know that 4 isn't. So 101 divided by 5 is 20.2. So 5 isn't a factor. Now if we didn't already know, that would tell us 5 and 10 are not factors. Now, that just leaves us with one more potential factor under 10 to try, which is 7. So, 101 divided by 7 is 14.4. So, 7 isn't a factor. So, what have we shown? Well, we've shown there are no factors except one that are less than or equal to 10. So that tells us then, without having to try them explicitly, this tells us there are no factors except 101 that are greater than or equal to 11. So, therefore, 3-dot triangle in maths means therefore 101 is prime. End of proof. We've done it. Jobs are good. Okay, example 3, we're getting a bit tricky now, we get algebra involved. So, the conjecture is for integer values of x greater than 0, f of x equals x cubed plus 5x plus 1 is odd. So, how in the world do we prove this then? There's an infinite number of values that x could take. So, can we do this by exhaustion? Yes, we can. We need to consider two cases. X, being an integer, can either be x can be even or odd. So we need to consider both cases. So we're going to go for the first case first. Makes more sense to go for the first case second. So, first case, x is even. Okay, well, if x is even, then we can say x is equal to 2k, as long as k is an integer. So, as long as k is an integer, I guess we should say as well, greater than 0. So, as long as k is an integer greater than 0, x equals 2k will always give us an even number. So, if we then substitute x equals 2k into the expression, then we get f of 2k will be 2k all cubed plus 5 lots of 2k plus 1 on the end. So, if we expand and simplify, 2k all cubed is 8k cubed plus, well, 5 times 2k is 10k, and then plus 1 on the end. Now we can factorise the algebra a tiny bit. Between 8 and 10 we have a common factor of 2. So we can write this as 2 lots of 4k cubed plus 5k, and then we got plus 1 on the end. So let's take a peek at what we've got here then. So k is an integer greater than 0. So the stuff in the brackets might be even or odd, but whatever we've got inside of the brackets, when we multiply it by 2, that's always going to be even. Now, when we have an even thing and we add 1 to it, we get an odd number. So what we can say so far, the conjecture is true for all even x. So it's true for all even x. Now we need to prove that it's true for all odd x. Okay, so for case 2 then, x is odd. So what we're going to say now then is that x, if it's odd, is equal to 2j plus 1, where j is greater than or equal to 0. So here, if j was 0, x would equal 1. Remember, the definition of x is that it is some integer greater than 0. So j can be greater than or equal to 0 for x to be able to be 1. Okay, so whatever j is, then 2j plus 1 is going to be odd. So what we need to do now is find f of 2j plus 1, which is going to be a little bit muckier than what we did up above. So we're going to get 2j plus 1 cubed plus 5 lots of 2j plus 1, and then we've got a plus 1 on the end. So we need to expand 2j plus 1 cubed. Now expansions like this are going to get easier for you soon when we come to something called the binomial expansion. for now, let's go through it. How we would at GCSE. So 2j plus 1 cubed is saying 2j plus 1 times 2j plus 1 times 2j plus 1. So let's first of all do 2j plus 1 times 2j plus 1. That's going to give us 4j squared plus 4j plus 1. So then for 2j plus 1 cubed, we want to do that. So 4j squared plus 4j plus 1 times 2j plus 1. So what we're going to get for that then? We are going to get 2j times 4j squared is going to give us 8j cubed. Let's see what x squared terms we're going to get. So we're going to get 4j squared times 1, and we're also going to get 2j times 4j squared. So we're going to get 12j squared altogether. And then for the j terms, we're going to get 4j times 1, add 2j times 1. So we're going to get add 6j, and then 1 times 1 is 1, and the end like that. So that is our 2j plus 1 cubed. So now we've got that plus 5 lots of 2j plus 1 plus 1. So if we now write those bits in, we've got plus 5 times 2j is 10j, 5 times 1 is 5, and then we got the plus 1 on the end. So let's simplify this lovely expression. We've got 8j squared, and we've got 8j cubed. Then we've got 12j squared. Then we've got 6j and 10j, which is going to give us 16j. And then we've got 1 plus 5 plus 1. So we've got plus 7 at the end. Okay. So what we can do here now, again, we can factorise the algebra a little bit. So we can take out a common factor here of, actually 4. So we can say we've got 4 lots of 2j cubed plus 3j squared plus 4j, and then on the outside we've got plus 7, like that. So again, whatever value of j we substitute in the bracket part could be odd or even, but if we then multiply it by 4, which is even, we know we're going to get an even number. So then again, if we then add a 1 to an even number, we get odd. So we've now just proven f of x is odd for all odd x. Now remember, up above, we've already proven f of x was odd for all even x. So we can now say f of x is odd for all x greater than 0, where x is an integer. So that was a tricky bugger, but we've got that. Hope you followed it. One more example then. Okay, the final example for this video then. Now I highly doubt you will see anything like this, particularly in year 1 of A level. But I think, well, first of all I wanted to do it. It's something I did at uni, so it's nice to revisit that. And also, it shows us the power of proof, because we're going to be dealing with infinity here, sort of, a bit. So, we want to then prove that every perfect cube, so basically a cube number, is either a multiple of 9, is one less than a multiple of 9, or is one more than a multiple of 9. So, this seems like quite a daunting task. There are an infinite number of cube numbers. How do we prove this? How do we make sure that we test every single cube number? Well, we need to think of an exhaustive way to treat every single number. So, we're going to use 3 cases. Every number, every integer, I should say, is either one a multiple of 3. Now, if this is the case, let's say our number is n. We could call n 3k. If it's a multiple of 3, then n can be some number 3k, where k is an integer 2. So that's case 1. Or case 2, it can be 1 more than a multiple of 3. So, if this is the case, we can call our number n 3k plus 1, and then for case 3, a number can be 1 less than a multiple of 3. So, if that's the case, then we would say n is equal to 3k minus 1. So, what do these 3 things mean then? It's got very algebraic all of a sudden. Let's go through some integers. 1 is 1 more than a multiple of 3. 3 times 0 is 0. 1 is 1 more than 0. 2 is 1 less than 3. 3 is a multiple of 3, so 2 is 1 less than a multiple of 3. 3 itself is a multiple of 3. 4 is 1 more than a multiple of 3. 5 is 1 less, 6 is a multiple of 3, 7 is 1 more, etc, etc. So every number can be described using one of these 3 definitions. So now we need to take care of each of these 3 cases and show that we either get a multiple of 9, one more than a multiple of 9, or one less than a multiple of 9 when we cube each case. So we're going to start then with the first case. So the first case is n is a multiple of 3, so n is 3k. So remember, we're dealing with perfect cubes, so we want to find what n cubed would be. So n cubed would be 3k all cubed, which would give us 3 cubed k cubed, which is 27k cubed. Now 27k cubed can be written as 9 times 3k cubed, like that. So this is indeed a multiple of 9. So we can make a big tick there. Case 2, which way around did we do it? What was our case 2? 1 more than a multiple of 3. Okay, so case 2. So for case 2, n equals 3k plus 1. So n cubed is 3k plus 1 cubed. So if we expand that out, now by all means, if you want to practice your triple bracket expansion, go ahead, or just take my word for it here that we're going to get 27k cubed plus 27k squared plus 9k plus 1. Now we can factorise the algebraic part of this a little bit. We can write this as 9 times 3k cubed plus 3k squared plus k, and then we've got the plus 1 at the end. So this whole thing is being multiplied by 9, so this is indeed a multiple of 9, then the plus 1 makes it 1 more than a multiple of 9. So it works for the 2 cases we've done so far. If n is a multiple of 3, then n cubed is a multiple of 9. If n is 1 more than the multiple of 3, then we've just shown n cubed is 1 more than a multiple of 9. We now just need to play around with our third case, where n is 1 less than a multiple of 3, so n is 3k minus 1. And then n cubed is 3k minus 1 cubed. So n cubed is again going to be 27k cubed Then we're going to have 27k cubed. We're then going to have minus 27k squared plus 9p and then minus 1 at the end. So we can factorise the algebra again. We've got 9 lots of 3k cubed minus 3k squared plus k, and then we've got the minus 1 at the end. So again, this is a multiple of 9. So the whole thing with the minus 1 at the end is 1 less than a multiple of 9. So we've proven it works for our 3 cases, which are exhaustive for every single number greater than 0 for n. So we have proven that perfect cubes are always either a multiple of 9, 1 less than a multiple of 9, or 1 more than a multiple of 9. Now that was extremely difficult for the start of A-level maths, so don't worry if that seems a little bit daunting. Maybe come back next year, watch this again, it might make more sense. Okay guys, that's it for this video. Hope you've enjoyed it. Take care. In the next video, we're going to channel our inner Sherlocks and do some proof by deduction. So we're going to be doing some deducing. Cool.